Hey guys, welcome back to AlgoYogi. We are doing tree series right now. Our next problem in the list is unique binary search trees. Let's visit the problem on LeetCode, which is quite really simple. The description I meant. Given an integer n, return the number of structurally unique BSTs. So we are given the number n here. For example, here it's given 3, and now we have to return using those 3 nodes. So basically we're given the integer n, and let's say n represents the number of nodes that we can use, and let's imagine they are all unique. If they're not unique, I think we might create like a lot of similar trees using those nodes. So it's like given it's already mentioned over here. Yes, it's already mentioned. So which has exactly n nodes of unique values from 1 to n. That has to be there. Okay, that has to be there. Well, I think I was reading it wrong, but anyways, cool. Okay, let's dive into the solution now. All right, so tell me, if I ask you how many unique binary search trees can you create if I give you my n as 0. So that means 0 nodes are given. How many unique binary search trees can you create? 1. You can create 1. Why? You can return null. Right? So that means 1. If I tell you, if I give you 1 node, that means you can create 1 unique binary search tree. How about when I'm giving you n2? That means what? Now we have to like take like few examples to understand it. So now if I'm taking n equals to 2, that means I have 2 nodes, which could be let's say it's given in the form of array, or maybe like I'm just creating an array. So that means 1 as a node and 2 as a node. Using these 2 node values, I'll have to create the unique binary search tree. So what if I choose, so now in order to create the binary search tree, you'll have to choose root, and then you have to choose left subtree and right subtree. All right, so if I choose 1 as my root, that means what? Now I have chosen this value. This is already gone from my list of nodes, n nodes. This is gone. Only remaining value is 2. So what I can do is I can only place this particular value in the right of my current chosen root. Why? Because since I created this array, everything after my chosen root, it would be greater, so that it has to go in the right of my current value, or in BST. That's the property of a BST. You guys already have gone through it. So I can only place this node over here, right? And the same way if I choose 2 as my root, and maybe let's just call them values for now, an array of values, we are creating nodes using those values. So what can I do now? So this side can only be taken by whatever is in front of my chosen root, which is like I'm placing this array here, so that this array will be used to create further subtrees in the left. Right, it's nothing, so it will be null. Null means from that side there will be 0 number of one node that can come, which is null. So this side will be none and this side will be none. So tell me, how many unique nodes can we create here? The answer is 2. Let's move forward to a little more complicated example, which is n equals 3, which is also our example here, and let's find out if we calculate the output right. So when I have 3, so let's create the array of values that can be used to create the unique binary search tree. So let's say now again I can choose 1 as my root, I could choose 2 as my root, I could choose 3 as my root, and let's see how many unique trees we can create when we are choosing 1, 2 and 3 as root. So when choosing 1, I only have availability of having 2 nodes on right, because these are the only greater values that after choosing 1 as root are remained in the array. And we know using when n is 2, I can create 2 unique by BSTs. So basically this will return, so there is nothing unique we can do here, so the answer will be here to just 2. From here it will be 2. What about when I'm choosing 2 as my root? That means I can place 1 on left and 3 on right. So I'm not placing them as like creating them node, just I'm giving you guys an option to figure out like how using just one value, how many unique BST, like unique leaf or unique left and right subtree you could create. So from here is just the answer is like this is the only answer, so it will be 1. And in 3 that will be similar to 2, except the fact that this time we don't have anything on right, but left would be 1 and 2. We could choose these two values. So we could choose left and either now here it could be just you choose 1 as root or 2 as root, that also gives you answer 2. So now in total we can create 5 unique BSTs, and you guys can already see over here these are those different 5 unique BSTs. Now what are we actually seeing is given n, and we are on the given node values we are basically choosing if choosing like one root, and then based on that root we are basically finding out how many values will go on left and how many values will go on right, and depending on that we are basically calculating how many unique BSTs we're creating. So that what's actually happening is we know how many values are going in left and how many values are going in right, and depending on that we're basically calculating the combinations. And in combinations we know that given these values, let's say this side has 2 values and I know this side is nothing, but still if nothing means like that remains exactly the same, so it's just one value which is none. So that means here it was left into right number of values that could be placed after choosing 1 as root. So and we have done the same thing over all of these. So from here it was 2 into 1 that returns 2. Here it was 1 into 1 that returns 1, and here it was 2 into 1. From this side nothing means just 1, and then it returns 2. And after joining them, like we were basically returning 5 as answer. So we're going to do the same thing. It's just it will be a recursive function, and for each of the value it will be basically calling left and right the DFS function on left and right subtrees, and again again go to the base case, which will be here, that is either n equals to 0 or n equals to 1, or we could just combine them saying like they're less than or equals to 1. That means we know like that would be returning one unique BST. Alright, so let's just write the solution now. Quite really easy to understand. Later we will be doing a more complex problem on the same topic. That is, next time we will be returning the unique BSTs. Right, so what we're going to do is have like a let's call the function DFS, that is going to take n, and now if n is less than or equal to 1, that means I'm returning 1. Otherwise my total trees, or let's call total BSTs. Right now it's, let's say, call it 0, but 4. Now I'm going to choose a root from 1 to, like, all of them, 1 to n plus 1, because 0 we are not choosing as a value right now. So for I in range, for I in range 1 to n plus 1, and then now for left trees it would be, I'll call DFS on I minus 1, because that many trees will be in the left of the particular root that I'm choosing. This I could even call it root, so that will simplify things for us to understand. So root minus 1, root is the number, it's the node that I'm currently processing. All right, and for right it would be, number of trees on right would be, it would be n minus root. So far, like, I have covered root number of indexes, so, and I'm n minus that root number of indexes is the remaining values that could also become root, that will be going to the right subtree of particular root that I've selected. All right, then I can add basically both of them to my answer, and by multiplying, so that we can add the combination, the number of combination that we can make using that many nodes on left and right subtrees. And we have seen it in the explanation why we're actually doing it. All right, and then finally we can just return total BST. Okay, now let's return DFS on n. Okay, let me zoom out, try to run our solution. Okay, there is some issue, and that is why it's returning 1. It should be plus, yes. It's not just, it's updating those values. So all right, see, now it runs fine on the examples, but this is not an optimized solution, because right now it's exponential time complexity 2 to the power n, and because we are calling DFS again and again, for n number of times twice, so 2 to the power n. But we can memoize it. We don't have to actually, for each n as they are reducing, like for n, when n is equal to 5, and when my index is on 3, then I'm calculating for 2, n equals to 2 and n equals to 3 on left and right side. That I don't have to do it if I could use memoization here. So what if I have a dictionary, and before returning my answer, I'll just save it in memo. So memo for particular n that I'm calculating that, and I'll just place my total BST over here, and then I'll just return memo n. And also that will not just solve the problem yet. It's before I start calculating for that particular n, I have to ask this memo if n key exists in the memo. If n in memo, then instead of for that number of n, I don't have to again and again choose those nodes and calculate left and right subtree, multiply them and add to my total. I could just simply return it from my memoized dictionary, that is memo, and return for n. All right, so that should be accepted. All right, so let's try to submit it. Did something happen? Why is it taking so long? I forgot to add the return statement over here, so let's submit it again. Cool, 100%. All right, let's write the time complexity, and that is big of n. N is the number of nodes, number of unique values that are given to be calculated, right? And space complexity will also be same. Since I'm storing the values in memoization. Okay, let's go back to AlgoYogi and mark this problem also solved, and see you guys in the next problem. Right, bye bye.